You can start.
Okay, hello everyone. Welcome to USACM Student Chapter Seminar Series. This is our first session from this monthly series. The first Friday every month, we are gonna have the seminar, and please feel free to join to the Student Chapter Discord channel through this barcode, and also our seminar based on the if the presenter is okay with that, we are gonna record the seminar and we will put the video on chapter YouTube channel. Just if you are interested to present your work, please reach out to us through this email, which is here, studentchapter@usacm.org. And we would be very happy to see your nice work. And if you have in general any question, please feel free to reach out to us through the Discord channel or through the email. Today, we are pleased to introduce Jan-Henrik Bastek, a PhD student from ETH, and particularly from Professor Kochman Group. He is gonna introduce his recent work on inverse design of nonlinear mechanical metamaterials via video denoising diffusion models. So without further ado, Jan, floor is yours.
Again, thank you to the USACM student chapter for inviting me. And as Bauder mentioned, right, I'm a PhD student based in Switzerland, in Zurich at ETH. This is my advisor, Dennis Kochman, who you might maybe have interacted with in previous conferences. As you can see, we're a decently sized group. We don't just work all the time. Sometimes we do go out and enjoy the Swiss countryside. And actually, we're located very close to the main station of Zurich. So if you're ever nearby, there's really no good excuse to not briefly come by and say hello. The title of my talk is Inverse Design of Nonlinear Mechanical Metamaterials via video denoising diffusion models. It's quite a bit to digest, but let's start very simple. Let's start by focusing on these middle words here, mechanical metamaterials. And this is, I guess, a mechanics audience, so you know what these are about, but let me briefly spend 1 or 2 minutes to make sure we're all on the same page. And to understand mechanical metamaterials, let's first understand ordinary materials. And we all know, right, ordinary materials derive their properties from nothing else than their composition and their microstructure. So if you have this block of material and you zoom in far enough, you will see some kind of structure arising. And this is in the end, the structure constitutes in the end the macroscopic response that we are typically interested in, which kind of dictates why metals are very strong or certain metals are lighter than others. And there's a lot of course, in the last decades, a lot of mechanics, chemistry, material science has kind of focused on understanding this relationship between the microstructure and the macrostructure. This is very nice, of course, but also limiting in a certain sense, because let me go back. If you are a designer and let's say you want to have a material with a certain target property, that means you kind of have to hope that the materials that exist in nature offer you hopefully something that's very close to your desired response. But this catalog that nature offers, of course, there's no guarantee that you will find something that really reflects what you want to have. And this is where mechanical metamaterials come into play. They look the same from the outside. So if you're just look at a mechanical metamaterial, you might look the same than an ordinary material. But if you zoom in this manner, you will see that on a certain microscale, so this could be in the micrometer range, you will see some kind of periodic artificial structure arising. And this one is man-made. We can decide how this kind of structure looks like. In this case, it's some truss structure, which is based on a certain unit cell that you just tessellate in all 3 directions in space. And we in Zurich, have spent a lot of time on understanding the relationship between, again, the effective macroscopic properties and the corresponding unit cells in both directions. That's the important part. So, of course, on the one end, if you have a certain unit cell, you can find very nice methods that give you the macroscopic response, but also then the inverse problem, which resonates with what I mentioned before. If you have a certain target response, what kind of unit cell gets you there, right? So this really goes in both directions, and you see it again, a bit more highlighted. So we have the modeling part, which is, you can understand as the forward map, given a certain unit cell or a certain metamaterial parameterization, what are the effective properties of this parameterization? You can always do something like finite elements, but I mean, you can see here, if you kind of try to discretize this with finite elements, this will not be very feasible. So there are very smart ways to do that. But then also the inverse design part, given a certain target property, what is the corresponding unit cell? And this is not necessarily a unique map, right? There could be different unit cells that could give you the same target response. And it is for this reason, and among other reasons, that this inverse design, so this red arrow, is actually even more challenging than the forward, the blue arrow. And this is what this talk will be about. I mean, it was in the title. We're focusing on inverse design. And this inverse design is a very good setting for these data-driven models, whatever they may be, because we've seen a lot of success with these models in very different areas, right, in computer science, but also now in engineering. And these are very good in learning non-trivial high-dimensional maps. And that's why we consider data-driven models here. Now, the focus of this talk will be the main novelty of this work I'm going to present here is kind of this part here. I would say there have been a few years where people have applied these models to do inverse design, but most models really consider linear target properties. By linear, I mean linear in the mechanical sense, so based on small strain kinematic measures, like the effective stiffness tensor, which you see here, which dictates just how stiff a material or a metamaterial is in a certain direction in 3D space. But this is based on linear theories, which are, of course, much simpler than full nonlinear theories and full nonlinear properties. And the goal of this work that I'm about to show you is to, well, move this a step forward and also do inverse design for nonlinear properties, so for finite strain measures. And briefly, what are we considering? So I would argue one of the most fundamental nonlinear properties in the mechanical context is just the stress-strain response in general, right? Which could look something like this. Maybe just briefly to give you some motivation why this is interesting, not just a nice academic problem. There are very diverse areas where people want a material that can follow certain stress-strain curves. One being biomedical implants, where studies have shown that if you burn your skin or you just damage your skin, doctors usually insert some scaffolds, artificial scaffolds that assist the regrowth of the skin. These scaffolds should, however, have the same nonlinear properties than the surrounding skin, as you can see here. And again, so this gives you some motivation, right? We need scaffolds that have a certain nonlinear response to fully assist the regrowth. Then, of course, there's energy storage, release. If you have impact, that's, of course, nonlinear. But maybe let me briefly also talk about soft robotics, right? It's this kind of emerging field in the last years, it got quite popular, which I would argue is born from the observation that the most successful robots that we observe are not these kind of rigid industrial robots, but rather something like us, human beings, right? And we have some inherent compliance. So if we grab something, we don't have very stiff, we don't have metal fingers, right? We have some tissue that is compliant, that gives us some kind of feedback on the structure that we want to grasp, and that allows us to grab an egg without breaking it, for example. And for advanced soft robotics, we also, of course, need advanced materials that can achieve this nonlinear property. This is a bit on the motivation side. Let's talk now about the actual framework. And if you think back on the title or what I mentioned before, this is a data-driven framework. So that means, of course, first you need data before you do anything fancy. And the first question to ask yourself when you do data-driven frameworks is how exactly do you parameterize, in our case, these mechanical metamaterial unit cells? In principle, there are a lot of things you can consider. And so trusses would be one example that I've shown you before. In this case, we do something very simple. I'm not saying this is very novel what we did here. It's very simple, pixelated parameterization of your structure. So you just, for example, here you could consider this as some material where the white pixel corresponds to some material A, and the darkened pixel corresponds to some other material, and then you get some kind of composite structure. There are advantages and disadvantages with this kind of parameterization. But one thing it is for sure, it's fairly general, right? You can kind of identify a lot of different structures. Of course, this depends on the resolution, but yeah, it's very general and has a lot of other advantages that will become apparent later. There's one problem. So still, let's say you have decided for this pixel-based design space. Still, if you just sample, let's say, these random QR codes and assign to materials or to material parameters to these different pixels, you will not get very interesting nonlinear responses, because in the end, you're just kind of averaging out the properties of these two different materials. But what we want in this framework is not just some kind of simple monotonous increasing stress strain response. We want very diverse responses, which is much more challenging, right? But you won't achieve this with this kind of structures. So what we instead do is, again, quite simple. We just consider Gaussian random fields to sample from. These are just like a 1D, like a 2D extension to 1D Gaussian processes. And they look like this hilly loss landscape of neural networks. At least that's what I'm reminded of. And what we do then is just introduce a threshold that we vary a bit. And everything above the threshold, we will just assign a material to. And everything below that will just be void. And the advantage of this is we have some other checks here to ensure that you can tessellate this and so on, but it's not that important. The nice feature is that you introduce some spatial correlation between adjacent pixels. Of course, this depends on the kernel and so on, but in general, you get much more interesting macroscopic structures, which have much more diverse effects than just these averaged out responses. So this constitutes our design space. We also need, we have the unit cells, but we also need the properties, right? So we need the nonlinear responses. And again, this is very straightforward. We consider the following setup. We do finite elements. We consider some kind of sandwich layout where we have a periodic tessellation in the horizontal direction. We apply quasi-static compression up to 20%. We have plane strain assumptions. We have some nonlinear material behavior that was calibrated on some actual structures. And what is important, we also consider contact. And that's actually a very tricky part. And this took me quite a while to implement this in a nice way. Why do we do that? Well, if you look at the following, this is what you get out of your FEM solver if you did set up everything correctly. And you see here the vertical stress distribution throughout the deformation process. And if you look at in the end, the effective response, which is just, you can just basically take an average of any, you can just consider a row of pixels and average it. This will give you the effective response. So it's very simple. But one thing I want to highlight is this non-smooth jump or increase here in the end, right? And where does that come from? Well, if you look closely at a certain deformation step, you see the outer parts of the structure also contributing against the deformation. And this gives you this, non-smooth increase in the end. And this is, so for this reason, I included buckling and I also included contact, really to have very diverse stress strain responses, right? Not just these monotonously increasing responses. And because we want in the end a framework that can, I'm not saying you can give any curve you want, but it should be able to leverage these non-trivial mechanical phenomena to get you close to this desired target response. And now here comes really the main novelty, and maybe, so what I'm kind of challenging here is something that might also be maybe helpful at some point in your research. So if you look at most of the work that is out there that has been published in the past years, people do the following. They want to train some kind of neural network, can have a very different form, can be a GAN, a variation autoencoder, or flow-based models, whatever. People typically do the following. They directly try to mimic the kind of inverse problem they want to solve. And the inverse problem just means you want a model that takes as input your target response and gives you as output the design that gets you there, right? So directly mapping, you want to obtain a map that brings you directly from the target response to the underlying design. And this corresponds here to the following red arrow, right? So you want a model that takes in the stress strain response, something like a 1D signal, and gets you some image that represents your undeformed topology. So we tried this, but I would argue this is not working for, this might work for linear responses, for simpler problems, but it does not work for nonlinear responses or for more intricate mechanics. And why is that? Well, if you look at it as it is shown in this slide, where the kind of what happens in between is darkened out, the model has no knowledge of what actually happens here, right? The model has to infer the relation of the nonlinear property to the undeformed topology all by itself. So it has to basically capture finite strain mechanics, including contact, elastoplastic material models, just by having this 1D signal and this undeformed topology. And this does not work. We tried with many different setups, but I would consider really state-of-the-art stuff, but it doesn't really work. So why not do the following? Actually, here I have it. Let maybe skip about that. It's not that important. So the natural idea is to do the following. Why not? We have all this data in the middle. This is what the FEM code gave us, right? We can store it and we have it, but we need to do these computations anyways to get from the topology to the response. So what if we just try to think of a way to pass all this information also to the model, and not just kind of the endpoints or the start and end point of this mapping we want to learn. And right now there will be a brief stop, so I won't talk about mechanics for maybe the next 5 minutes, but I want you to keep this kind of question in the back of your head, right? We want a model that meaningfully embeds or can learn this kind of response in between. And you will quickly see how this relates to the machine learning part. And I want you to remember that this is the goal. And of course, if we have a model that understands this relationship, we can trivially extract the undeformed topology, right? So this brings us to video diffusion models, which, if you think back on the title, was also one of the keywords, which have gotten very popular in the last, I would say, 1.5 years. So when I first presented this work, not many people knew about them, but I think nowadays it's really, they got very popular, right? And a lot of people have seen them on Twitter or I don't know where. Definitely, I think most of you have seen, right, these image generation models where you type in some kind of text prompt and you get out an image of that. And as you can tell, they have been extended to videos. Videos are, I mean, nothing else than a bunch of images stacked together with some kind of logical consistency between them. But I'm still, I must say, very impressed what these models can do. If I think 3-4 years ago, anyone would have showed me or other experts in the field what is possible in 2023 or even earlier, then I wouldn't have believed them. But let me stop talking and showing you actually what happens if you put in, for example, this text prompt into one of Google's state-of-the-art models. So here you have a happy elephant wearing a birthday hat walking under the sea. This is what comes out after maybe 10 seconds in this video diffusion model, which, I mean, I find very impressive, right? There's always the question, right, do these models just reproduce something they've seen in their training data? But in this case, I would argue it's very unlikely that this exact scenario was in any video the model has seen. Let me show you another example, which is this one, a glass bead falling into water with a huge splash, sunset in the background. And again, yeah, I think this is crazy. There's no notion of Newton's law or so in the models, right? Of fluid dynamics, Navier-Stokes, you name it. The model just sees data, and it still comes up with something that looks, at least to the layman's perspective, to my perspective, quite realistic, right? I mean, if you zoom in, there are probably some artifacts. It doesn't look 100% convincing, but it gets close, right? At least superficially looking at it, it looks very good. I think this was this video was one of the reasons why I consider these models, because you could also think of this as a fluid dynamics solver or simulator, right? It's probably, I'm not saying it's accurate, but just from the idea, it does something very similar, right? And well, this gave rise to the idea, why can we not leverage these kind of model classes to do actual, I'm not saying this is not scientific research, but research in the more natural, like in the natural sciences, right? And not use this for some kind of artistic exploration. I don't have enough time to talk too much about diffusion models, how they work. I'm happy to take questions later. These are a class of generative models, so they try to learn the data distribution. So you assume that you have a certain data set, a training data set consisting of a certain number of data points, and you assume that all these data points were sampled from some unknown probability distribution. You just hypothesize that this distribution exists. I think it's more of a philosophical question. Yeah.
I'm so sorry. We have just 2 minutes.
Oh, really? Then I really spoke too slow. And let me maybe skip this part, but I'm happy to talk to provide any details if people are interested. Let me maybe summarize in one sentence. So these are a class of generative models that are very successful in learning these data distributions, also when they are very complicated, which they are for video data, for example, and others. Let me skip that. Maybe one sentence to the architecture. So this is a typical unit architecture because we have this symmetric, typically in diffusion models, you map from a noisy data point to a slightly less noisy version of that. So the dimension of the input and output are the same, and you consider symmetric architectures. In this case, we have a 3D unit because you also have this temporal dimension, which reflects the video component. And yeah, I'm going to skip this. Happy to talk more about this if there are questions. Let me really skip to the results and to show you why we are so, or we're very excited to see what these models can do. So here you have what I mentioned at the beginning. You have a target response, which are these red dots. And now let's see if the model can actually predict a metamaterial that performs or like matches this response very well. And I also included the best match in the training data set to really see, can the model actually do meaningful generalization beyond the training data? So this is what the model predicts. And we train, so I didn't mention this, right? But I guess you made the connection that video diffusion models are a good candidate to train it on this video of finite deformations. And the model is trained also on the stress data, which you can see here, the vertical stresses, which constitute this effective response. And we see the model indeed, we can also, the nice thing is we can extract the effective response from this prediction because we can just average over one row of these stresses. This gives us the overall response of this predicted structure. And you see this in these green triangles. So the model thinks that it's very close to the target response, but it's just purely the model right now. To really make sure that this is true, we have to put it into finite elements. This you see in blue. And to our, not surprised, but to our relief, indeed, the FEM solution agrees very well with the predicted one. The nice thing is we can also convert it into the Eulerian frame, and there you get much more insights in what's actually happening and how this model has come up with a deformation process that reflects this response. So we have a very compliant response in the beginning, and you see it's like a purely rotational deformation in the beginning. And then at a certain point, right here, the model learns to introduce contact, and this is why we have indeed these stark increase in the effective response. Let me read. I know I'm running out of time, but I think this is the most interesting part. This is a probabilistic model, right? It models the probability distribution. It means we can sample every time from it. We can sample 1 million times from it, and we will get different predictions. So that's what, for example, you see here. Here we have this response, this target in red again, and we get three different predictions, which are all very close to the target, but look very distinct topologically, right? So this would give also the designer flexibility in deciding which structure he likes most. And to finish this, I also mentioned buckling. So what happens if we put a negative stiffness corresponding to buckling? Again, the model predicts something that matches this much closer than the best match in the training data set, which is again, very nice. But what is interesting, if you look at the predicted stress field and the FEM stress field, if you pay close attention, they're actually exactly the opposite. So if you just look at the relative L2 error or some error norm, you'll get very large values. But if you look in the Eulerian frame, this is actually what happens. So the model buckles to the left, finite elements buckles to the right, but this in the end is just like a coin flip, right? Decided by the numerical precision. So we cannot penalize the model for not following the FEM response. But that's where these probabilistic models are very good in, to have like this non-unique, to model non-unique solutions. Yeah, with that, I'm already at the end. Sorry for running a bit out of time and for skipping some parts. Again, we have, I just said it, right? We have a model that can do nonlinear properties, can include nonlinear, non-trivial mechanics such as buckling and contact to get there. And let me just highlight, if you do classical topology optimization, there's very little work that, for example, tries to introduce contact to do that. There's been now a preprint by Ole Sigmund, which was published, I think, a few months ago. But this is one of the very few papers, and I would argue it's not as complex as here. And my personal opinion is that the more complex mechanics gets, the better it is to rely on these very powerful models to obtain this inverse mapping, instead of doing like a direct kind of gradient optimization, which is more what classical topology optimization is. Yeah, let me finish here. So you can check out the preprint if you scan this. There's also the code and the data, it's all included. This will soon be out in Nature Machine Intelligence, so we're very happy about that. But again, most of the information is already out there. So thank you very much for listening on this Friday afternoon, and I'm very happy to take any questions if there are any.
Thank you, Jan. Very, very interesting presentation and topic. Yeah, Osama, go ahead. I think Osama has a question.
No, I was just doing the flapping hand exertion. I think there's a question in the chat. How do you ensure connectivity for tessellation?
That's a good question. So this is, let me just, my laptop is already on the weekend. It's a bit laggy. I think there are two questions hiding in this question. The one is on the data side, on the data generation side. How do we ensure connectivity? This is just by rejection sampling. So we just sample these random fields, which is very efficient. You can do easily. We just reject the sample if it's not, it hasn't ensured its connectivity. That's on the data generation side. On the model prediction side, you're absolutely right. There's no guarantee. We don't enforce anyhow that the output of the model must have this connectivity, right? The thing is, these generative models get so powerful, and namely, also, especially diffusion models get so powerful that they, in my experience, they're very good in capturing these kind of non-trivial features of your data space. So actually, if I sample from a model, I can give you an exact number, but it's very rarely the case that the structure will not be connected. Very rarely happens because the model has captured this feature of the data distribution very precisely. So there are certain edge cases where like you can push the sampling further outside the support of your training data. So you go into, like, you sample from a space where the model wasn't trained that well, then you might get predictions where the connectivity is not ensured. But typically, if you don't do, let's say, more fancy things, it's very rarely the case that these models predict you something that is not that does not have this connectivity. And very briefly, also, I'd never enforce. You can see we have this twofold symmetry. I never enforce that we have the symmetry in the model output. So the model puts out this image of this overall structure, which obviously has these symmetries, but this is not enforced. However, if you train these models, they get that. You don't need to enforce it. Also, it's very hard to enforce it because, I mean, maybe symmetry is still doable, but I'm just saying if these generative models are very powerful and they can capture these kind of features if you train them long enough.
Okay. We have another question. What was training data? Did you use FE simulation data for training? Yeah,
so the training data is exactly what I showed right here. It's basically the video of the structure under deformation and the corresponding property, which is the stress-strain response. And this was done by finite-elements. So it took maybe, I don't know, a week or so. We have 50,000 videos in the end with which the model was trained. One simulation took maybe 2 minutes. And so you need the video data and the corresponding labels, which in this case is the stress-strain response.
The person for previous question says, when you obtain the material through diffusion model, did you encounter any aberration in the connectivity, or the model failed proof in terms of connections? You can also look at the comment or the.
Yeah, I'm just looking at it. So I'm not sure what the difference to the previous question there is, right? So basically, like when you refer to hallucinations by the model predicting a structure that is not connected, then again, this is probabilistic. It will happen eventually, but it's very unlikely that it happens. So maybe in 100 samplings, this might happen once or so. Maybe if you could clarify if that's not what you mean, that would be appreciate this. There's another question from Marco. Oh, hi, Marco. Yeah.
How did you design the target response? And the second one is, did you perform a sensitivity analysis on the training data size?
So the target response is a good question. Let's skip to this. So it's a good question. What do you actually, how do you evaluate the model? How do you check for generalization capabilities of the model? The problem is that typically you don't know the boundaries of your property space. Even for linear elasticity, like the constitutive tensor, which can, in its most general form, has 21 numbers, even there we don't know the exact boundaries of this tensor. And here it's even more complex, right? You have this nonlinear response, which, okay, we discretize somehow, but I mean, you have to be realistic. You cannot do any like random response. There will be limitations, right? But the way we chose these responses is the following, and I think that's generally a good way to evaluate the model. What I did here is that I have the test data, I have the training and the test data set. Test set was not used during training. And I compare all the responses of the test training data set with the training data set. So for every single data point in my test set, I compare the closest match in the training data set. And then I select that data point in my test set that is the furthest away from any kind of response in the training data set. So we kind of get the response that is the furthest away from anything the model has seen, but we still have some, we know, since the test data set is coming from an actual structure, we know that this is actually a physical response, right? Because if you just draw a random function, I'm quite sure it won't be possible to get there with this design space, right? And regarding the sensitivity analysis, we did some work. I think we could actually get much better. I think the model is still undertrained in the sense it could see more data. So 50,000 data points is okay, but it's not great. I think we could improve the model actually if we trained it on more data. But this was done using Abacus, and I had only so many licenses, so there was a bit of a limitation. I think if you increase the training data set, the model would still perform better. But even if you have only like 20,000 videos, the model still performed all right. Like, I want to refer to the public. So in the once the publication is out in the supplementary, there is some information on that with the actual numbers.
Okay, the next question is from Osama. Maybe he can. Do you want me to? Yeah.
Yeah, sure. Go ahead.
Okay, so 3 questions. Do you see an improvement in matching the stress strain curve by training over more diffusion steps?
I guess, so are you referring to the time steps in the diffusion chain?
Yes.
So this is a very hot topic these days in the computer science community to accelerate the sampling process, right? So typically you train the models on, let's say, 1,000 time steps, then you have to go backwards during sampling, which is also 1,000 time steps. There's a lot of work in the generative AI community to accelerate this process, a very rich field, which was not the focus right here. So, because we just want to get this to work, but So to answer this question maybe a bit indirectly, I think you don't care so much how many training steps you use, how many diffusion steps you use during training. It's more about during sampling, right? It will just take longer if you have more steps. But there are a lot of methods to accelerate the sampling procedure. Actually, you can actually sample in one step by now, I think. And it will be a bit worse, but it won't be much worse. So there's a lot, because diffusion models are the hot topic, right? There's a lot of work going in that direction. And I would argue, yeah, I don't have exact numbers, but you need it. For the training, I would argue you need a decent, I think we tried 256 steps or something in that area. I wouldn't train it on 5 steps, right? But I think 100 steps would maybe be a bit worse, but not a drastic difference.
The second question is, have you tried this out on 3D models?
That's also a good point. I mean, we pretend it's 3D, right? But we only have plane strain. It's actually a 2D problem. I agree. I guess by 3D models, you assume a 3D structure. Is that what you refer to?
That's right.
Yeah. So I think for 3D structures, this pixelated approach doesn't make much sense. Like if you extend this naively to 3D, you would use voxels instead of pixels, but this doesn't scale well. I don't think the way to go is to use voxels in 3D. I would rather say the way is to consider different parameterization, such as the truss structures I've shown in the beginning. You can represent them as graphs, and they're very easy. Like graphs are very easy. It's almost trivial to extend them to any dimension. So I think these are actually better to, if you really want to do 3D, I would actually consider maybe switching the parameterization, because I think with voxels, it's you have videos and then you have voxels. So it's like a 4D, tensor.
Slight comment on that, like it should be dictated from the problem, because some problem cannot be approximated by truss. The parameter.
I mean, it depends what you want, right? What is your target property? We don't care so much about, if you ask the designer, what does he care about? I don't think he cares about how the structure looks like, the unit. So he cares about the property. So we should think of, can trusses, for example, get you to the properties that you desire? If they can, well, then it's fine to use them, right? But I would agree, of course, trusses have also limitations. But I think it's not feasible to do voxels with the current computational power we have to go through 3D. Maybe in 10 years, maybe you can just crunch it through like GPUs that are 100 times more powerful than today, but it's just a brute force approach, right? Yeah.
The third question is, are there any prospects for reducing the computational cost of training the diffusion?
Yeah, he answered that with the first one, so that's fine.
Yeah, okay. I think, but just let me one sentence to this. This work is focusing mainly on this video part and to extending this into nonlinear responses. There's again so much literature out there that tries to reduce computational costs for these models, be it during inference, which is what I mentioned, right, the sampling procedure, but also training. You can train these not in the pixel space, but you have like an autoencoder that maps the pixel space to a latent space. You do diffusion in the latent space, you convert it back. That's actually what these, I think the state-of-the-art video models I showed you before, I think they do it in a latent space. And also, I mean, there's so much literature out there and a lot of people are trying to speed this up. So definitely there are a lot of options. No?
I have maybe myself also a question. For that, like you said, like the left buckling and the right buckling, how do you sure that you haven't have such a like a right buckling in your training data?
So you're saying your fear is that the model just reproduces something in the training data set. But I mean, we've shown before, this could be the case, could happen. But we've shown in the target responses, right, with the red dots, that the model for sure can generalize. That's the proof for these very tricky responses. I've shown you the best match in the training data set. That had maybe an error of 50%, while the model could go to an error of 5%. So I think this gives you the proof that the model can meaningfully generalize beyond what it has seen in the training data. It could very well be that the model just kind of reproduces something it has seen in the training data set. It's a bit hard to, I mean, you can check it out. You can search for this, of course. We didn't really do it, but I think we've shown you the proof that the model can do some generalization, right?
The last one is, was the training smooth? Someone asked.
That's one of the advantages of diffusion models. Training is very smooth. It's much easier to train in GANs or autoencoders, flow-based models. Flow-based models, I guess, also easier to train, but not as expressive. So as long as you pick a reasonable hyperparameter choice, and there are a lot of, by now there are a lot of good repositories. I can also recommend some if you have, just like message me later. I can send you some good repositories that have a very decent version running. So if you take that version and adjust it a tiny bit, you will have a very powerful model there. And their training is typically very smooth. One advice I would give is to let them train long enough. Like the losses are very, in this models, you don't have a mean squared error loss in the end between some prediction and what the model predicts. It's a more indirect loss coming from the elbow of how you train these models. And sometimes the loss might not actually go much further down, but it still could lead to quite different performances of the model. So don't be fooled by the loss stagnating. This could still mean the model is learning something. And don't just, I don't know, let it run over the weekend and see if you get something useful.
Great. I think we are like a bit like more than what we expected in terms of time. It would be great if very quickly you show us like the repository, and if you have like some code to showcase or something like that.
Oh, sure. Let's hope my Zoom doesn't crash again. Can you see my browser?
Yes.
Yeah, so I don't think I'll talk too much about, like, if you're interested in this, we put up a nice repo which has all the explanations on how to launch the code and how to evaluate it. So it's also in the preprint, there's a link to this Git repository, but yeah, I would advise you to check it out. If you have any questions, then very happy to answer these, but I would leave it at that, right? Because I don't think you can, I think it's fairly well explained, and if you have questions, just let me know.
Very nice. Thank you for your nice presentation and making this great work open source.
No, thank you so much for having me, and looking forward to the next talks.
Sure. Thank you everyone for being here. Hopefully we are gonna have you again next month. Bye.